Hi, this is Andrew McLaren, and I'd like to show you honestly, my number one trick on chemistry and physics problems and how to double check your answers. Uh, Oftentimes, there's these problems using scientific notation where you've got very big or very small numbers, and you're having to multiply and divide them or combine multiple numbers. And these problems, a lot of students, they just plug it into the calculator and they have no idea if the answer they get is reasonable or um, close to what it should be. And I want to help you understand how to check those types of problems. So we're going to talk a little bit about why and what these things typically look like, these types of problems. Then we'll go over the steps and the logic and like what you're going to kind of be doing. And then we'll go over a couple example problems. So the reason that I wanted to teach you this is that as a tutor, I've seen countless students just make the same mistakes and not have a good idea of, for example, if you had a problem like this, to be able to estimate the value of k, like legitimately no idea how big or small this number should be given the numbers that we're plugging in. Just looking at that, you should be able to tell me roughly if k is going to be big or small. Is it bigger than 1, less than 1? Um, is it bigger than maybe 10 or 100? You should be able to answer that sometimes and get a rough idea of your k value, or at least the magnitude that it should be in. When we're talking about like place values, that's kind of like magnitude, like 10, 100, 1000. Um, you should be able to tell me roughly what place values these numbers should be occupying in the final answer. So it's very useful because most of the time when students had a problem like this, they would get their calculator out. They'd get their graphing calculator or whatever, and they would be trying to work on it. And I would just get an estimate faster than they could actually with get the actual answer with their calculator. Like I would look at this problem and be able to get a rough idea within 10% accurate using these numbers here. It's very useful to be able to get a rough idea of what your number should be, because then I use that to double check the student's work to see if the answer they gave was reasonable. And most of the time, what's going to happen is you're going to be doing something on your calculator with these numbers. And let's say that you're trying to plug this into the calculator. You might start with parentheses 1.2 and then up to let's say 10 up to the second power. Oh, hold on. Let's say that we've got, yeah, I did the wrong thing here. So we've got 1.2 times 10 up to the second power. So that's the first number, right? So what you want to do when you're entering these things into a calculator is, it's kind of annoying because you would have like parentheses and then times 10 up to the second power, end parentheses, and then times 5.6 times 10 up to the -1 power. Right? There's all these places that this could go wrong. If you forget one of these parentheses, that can mess things up. Also keep in mind that this whole thing is up to the looks like the second power. So if you forget to put that 2 on there, that's gonna throw things off, right? And so you've got all these things that you're plugging in, and it's super easy to forget one of your operations. Also, if you get all of that in the top and then you try and divide the bottom, if you forget to put this stuff in parentheses, yeah, you'll divide by 2.3, but you'll end up multiplying by like the 10 up to the second power. It's very messy. There's a ton of places, like if you forget that parentheses there, where you're gonna get something that's, instead of making the k much smaller, this 10's gonna end up making it much bigger. And so you got to be very careful when you're doing these calculator problems, and being able to get a rough idea of what your answer should be allows you to check your answers very quickly. So the trick that I want to show you, basically you need to have the numbers written as scientific notation, and then you're going to split the numbers up into the coefficient in the front for the scientific notation, and then the 10 up to its exponent, which is going to show the magnitude or just how big or small these numbers are. And then what you do is you multiply the coefficients, and that's going to give you the number that ends up being in the front. And then you're going to end up combining your exponents using your exponent rules. And I've got a couple of them shown over here. If you don't know your exponent rules, very, very useful. This is going to save you a lot of pain if you're taking like AP Chem or AP Physics. And then you end up combining these, and you might need to change the like the 10 exponent it's up to, and you can do that by changing how big the coefficient is, and then also changing that magnitude. So let's go ahead and show you what this kind of looks like with this problem right here. So what you need to do is you need to take your numbers that are kind of in the front here, and this is actually, honestly, without doing anything with the magnitude, one of the easiest things to do is just combine these numbers that would go in the front of the scientific notation, and that's going to give you not your answer, but the numbers that go in the answer at the least. So all of that kind of goes in front right here. So we've got the 1.2 times the 5.6, and there's actually kind of like two of these, so you're kind of multiplying by two of those 5.6s, right? So you've got those the top right there, and then you're gonna have 2.3, and yeah, it's kind of like we've got three of those, right? It's that repeated multiplication. And then we've got another 2.3. And just doing this, and combining these numbers, your final answer is going to look kind of like that. So if you had like the 1.2 times 5.6 times 5.6. Oh, actually, hold on. Something weird's going on with the previous line. 1.2 times 5.6 times 5.6. And that's going to be on the top. That's 37.62. And then on the bottom here, I would usually just do rough estimates of this, because I'm just kind of doing a rough estimate. So this is 12.167, but I would usually estimate this because I was just trying to get a rough idea of what this number should be. I might look at this as like 1 times like 5 or 6, which is like 5, maybe 6-ish. Let's go with 6. And then times 5, that'd be like 30-ish on the top. So I'd tell myself I've got about 30 on the top. I've got 2 times 2, maybe 4, times another 2, that's 8. So you've got like 30 over 8, or about 3 or 4-ish. And that will give us a rough idea. So this is about 3 or 4 maybe, but it's, if we actually did the calculator work, we could figure that out as 37.62 divided by 12.167, and it actually is exactly 3.09. Let's go with 197. So we could say that, I mean, given our significant figures, it's going to end up being to 2 sig figs. So whatever answer is going to be, it's going to be like 3.1 times 10 up to some sort of power. So that's one thing to not even worry about the exponents, but just kind of know how you combine the numbers. And then you use your exponent rules here to look at these guys right here. So you might say like, oh, this is 10 up to the 2, this is 10 up to the -1, and then this is 10 up to the 2 here. But remember, we've got these exponents as well, which is, you got to keep that into account. So be careful there. So all of this is kind of being multiplied. Like this was equal to that, right? And so this is kind of like what's kind of going in the front, and then what's going in the back is that you've got 10 up to the second power. And then it looks like you've got 10 up to the negative 1 power, but it's being multiplied by 2. So that's the same as 10 up to the negative second power. And so you've got this plus, and if we wanted to, you could do like the minus 1 times 2. Right? And that's kind of accounting for that because you're going to have to multiply the minus 1 by 2 because there's 2 sets of that. And then we're also going to be, if you think about this, this is in the denominator. So you can subtract what's in the denominator. And that this is 2 times 3. Because this, you could rewrite this even. This whole thing could be rewritten. So I just kind of want to show you this really quick. Another way of writing out these numbers just to show you the exponent rule and how it applies. So you could say, instead of dividing by that, you could multiply by the inverse. So you could multiply by this number, but it's going to need to be a negative 2. Like this is just a kind of one of those things. You gotta need to have that be the minus 2 right there. And so you have to be kind of thinking about it in that regard. So you could bring it kind of down in front like that. So we now know if we do all of that math, we should be having some number times 10 up to, it looks like 2 plus another 2, that's 4. Or actually, no, this is minus 2. So that's 2 minus 2, so that's 0. And then minus 6. So I've got 10 up to the minus 6. So this final answer, like the answer, if we do this on the calculator, I bet is 3.09197 times 10 up to the minus 6. I bet you that's what that k value is. But let's go ahead and try and double check that this answer kind of makes sense given what we were plugging in. So I knew that I had something that was kind of big, but it was being multiplied by something kind of small, and they should kind of cancel each other out in terms of the magnitude. So that kind of makes sense. And then I knew that I had something kind of big in my denominator. I had 3 sets of that, so it's going to be really big in the denominator. So yeah, the k's magnitude should be pretty small. That does kind of make sense to me. Let's double check it with our calculator work, huh? It's always a good thing to confirm these calculations. So we got 1.2. I'm going to try and show you how I would do this on the computer. It's been a while since I've done these types of calculations on an actual calculator, but this is kind of what you'd see on the top. This times, hit the wrong button there somehow. So we've got that times 5.6 times 10 raised up to, it looks like, a negative 1 power. And then that is being raised up to the second power. So that's the top right there. Yep. So if I did that and I actually calculate that top part, that's actually that 37 that we calculated earlier, 37.632. And then let's calculate that denominator. So we've got 2.3. And yeah, I would honestly just calculate your numerator and denominator separately, then combine them later. It just helps with keeping track of some of your work a little bit sometimes. So we've got the 2.3 times 10 up to the second power. Okay. and that is being raised up to the third power, it looks like. Okay, hold on. What did I do weird there? No, actually, I think that that actually is correct because you see that these numbers are those numbers right there. It's just the we haven't got the magnitude taken out right yet. So this is 1.2167 times 10 up to, it looked like it was actually 10 up to the, what is that? 1, 2, 3, 4, 5, 6, 7. So is this up to the seventh power? Just want to double check that. So this would be the 0th power. If there's 1 there, this would be 1. And then 2, 3. Is it the 6th power? Is it the 6th power? I think it might be the 6th power. Yeah, I think it's the 6th power because if we go. It's actually, no, it is 10 up to the 7 right here. But if we wanted it to be 12, like if we wanted to make this 10 times bigger, you would have to make this 10 times smaller by making that 10 up to the 6th. So yeah, that does look like that's correct so far. And so if we plug this into the calculator, if we have 37.632 and we divide that by 1.2167 times 10 up to the 7th power, we get, hey, look at that. We got our 3.0929, looks like is what we're calculating, times 10 up to, isn't it the negative 6th? So it looks like the decimal came out slightly different when we, if we kept on going out a little bit further, but it's very, very close. So you can kind of see that this does actually work out. And yeah, it took me a little bit of time to work through that and think through that, but I was just trying to write out each thing so you could see it clearly with the color coding. And so you can kind of see that this is a really nice way of double checking your work. Now, if I was trying to do this quickly, I would just roughly look at this and say, is this k gonna be like bigger than 1? Like, is the numerator bigger than 1, or is the denominator bigger than 1? And to do that, I would just look at my magnitudes and kind of see how they're being combined. And I would see like, okay, these kind of cancel each other out in terms of how positive or how big or small the number is, like the tens. And then this is going to make it so that this k value is pretty small because the denominator was fairly large. So you should get a rough idea there of that number. And then if you do a little quick combination of the magnitudes, then that gives you an idea of, okay, should this be 10 up to the negative 8, 10 up to the negative 4? And that helps you double check a lot. Because if you combine your numbers kind of weird, oftentimes this thing is, the magnitude's like 100-fold too big or too small with these types of problems. And this also works not just with like k equilibrium, but this works with pretty much any problem that involves scientific notation where you're multiplying or dividing. And there's a lot of that in physics and chemistry. So this trick is really useful for when you're combining very large and very small numbers and you want a quick estimate to see what your answer should be. Now, let's say that you have some force, which is equal to mass times acceleration. It doesn't matter if you don't know the science behind this. You can focus on the math here. But let's say that you've got some mass that, say, maybe it's 500 kilograms. And you've got some acceleration. Maybe it's like, it's accelerating very slowly. Let's maybe say 0.15 meters per second squared. Those are just the units there. So we've got the 0.015 and we've got 500 kilograms. They're being multiplied by each other. And, you know, a lot of students, they could probably get an estimate for this. But if it was a much larger number, a much smaller number, they might struggle, right? But not if you know your exponent rules. I'll show you in a minute. But if we look at this, we could rewrite this as 5 times 10 up to the, what is that, the second power. And it's being multiplied by 1.5 times 10 up to, I think is this -2? 1, 2? Yeah, -2. And this is just the units. And so if we're trying to do our little trick, what we can do is we can say we've got 5 times 1.5, and our final answer, it doesn't really matter how big it is ultimately, but it should have a 7.5 in there, somewhere in there. So if we look at our tens though, we have 10 up to the second power multiplied by another 10 up to the second power. Which is the same as writing it kind of like that. And also, if you're just kind of curious, what we've just done is we've rewritten this fraction. You can think of this as the 10 up to the second power times 10 up to the -2 power. And that's being multiplied by the stuff right here. Right, we've just rearranged things slightly when we've written it like this. Like we've taken the numbers in the front there, and then you've taken these numbers in the back here as well, and then you've just applied your exponent rules to combine the tens, right? And so if we do that, we've got our 10 and up to the second, 10 up to the -2. Those cancel out, so this becomes 10 up to the 0th power, which is 1. So 7.5 times 10 up to the 0th power is 7.5. And this would be newtons because this is a force. So yeah, this works kind of nicely with this problem. Let's try and do a different problem, but it looks very, very, very similar. So if we, instead of doing those numbers, maybe we had some weirder numbers that you're not so familiar with. Maybe we had F is equal to m times a. Maybe let's say now the force is 5 times 10 up to the 8th power newtons. And then our mass is going to be 2.3 times 10 up to, let's say, the 3rd power. And this is going to be kilograms, and that's equal to whatever acceleration we're experiencing. So we've got some mass, we've got some force. We want to know roughly what this acceleration, how big it should be. Now I just look at these and I see this is 10 up to the 8, this is 10 up to the 3rd power, and know that A should have like 10 up to the 5th power or something around that. It might be a little bit different if these end up combining in a way that doesn't work out, but it looks like it should work out kind of nice for us. Actually, you know what, I'm gonna make this, yeah, we'll work with this as it is. Let's say we've got, if we rewrite this, we can divide both sides by the 2.3. And so A is going to be equal to its first number divided by that second number. Right here, something like that, right? And so if we have a problem like this, you could have your numbers in the front. You've got the 5 over 2.3, and then you're multiplying that by the 10 up to the 8th power minus the 3. So you got to know these exponent rules. If you know these exponent rules, it it makes these problems pretty easy. So this is 10 up to the fifth power, and that's going to be 5 divided by 2.3. So I know that's around 2 to 3. And so if I was trying to do this problem without plugging in any numbers, I would know that this, like 5 divided by 2.3, is around 2 or 3-ish, and that it should have a magnitude of 10 up to the fifth power. Like, it's pretty quick to do that and get a rough estimate without figuring out the actual numbers. But you can also do the math with the numbers and get the exact number. This should be red because we're trying to keep that stuff red. Oh, nope. And then if I'm trying to keep this to 1 sig fig, this is going to be actually 2 times 10 up to the fifth power. And you could write that out in its scientific notation as well. One thing to keep in mind is I'm going to copy this whole problem, but tweak it ever so slightly. Let's say, now you wouldn't really write it like this, but let's say that you had one of these problems and you had like 25 divided by like 2 or something like that, and times 10 up to the third power. What you would do if you had something like this is to write it in scientific notation. That, well, let's say this is going to be like 12.5 times 10 up to the third power. To write this in scientific notation, you need to make this 10 times smaller. So this needs to get bigger, right? So this then needs to go up. So if you end up making this smaller, this needs to be bigger. And so you move the place value over here, and that just changes the number in the exponents there. And so if you had something like this, you could say that that's 1.25 times 10 up to the fourth power, which is the same as 12.5 times 10 up to the third power. You've just moved over the decimal place here. You've made this 10 times smaller, so you make that 10 times bigger. You're just moving where the magnitude is really kind of seen. So just be careful. If you end up combining numbers in the front that give you something bigger than 10, you're going to need to move things, the place value over. Or if you got something that was like smaller than 10, you might need to move the place value over, right? So you might see that in some problems kind of like this. Maybe, yeah. You could imagine a problem like that, I hope. So let's say that you're looking at a really big problem. I'm just going to try and show you a couple more examples of this. I've actually worked this one out already a little bit. So if you have the force of gravity, here's the formula of gravity right here. And you can see that it's similar to that formula. We can actually calculate the acceleration of gravity, which we know on the surface of Earth is 9.8 meters per second squared. And that's, you get that from combining this gravity constant times the mass of Earth all over the radius squared. And so here are the values, and this is for the distance of the radius of the Earth if you're standing on the surface of the Earth, okay? So you could imagine that if you have these numbers and you plugged it into this equation, you've got something that's around 6 going in there. You've got something that's around 6 going in there. And you've got something that's actually a little bit bigger than 6, but let's say it's around 6 going in the denominator. And so if I look in the front, I'm essentially having 6 times 6 all over 6 squared. So think about that. That's basically 1. So I know that my answer is going to have something where the front is like kind of close to 1 whole in its the coefficient. Like it's not 2 or 3 or 5 or something like that. It's probably around 1. And then what's really interesting is if you look at these exponents here, you've got 10 up to the negative 11 right here. So let's actually just rewrite this whole thing so you can kind of see it. We've got the force of gravity right here, which is equal to that first, that number right here, being multiplied by this number right here. And that's all over this number being squared. So we think about this number in the bottom here. You got this times that, and then this is being squared. It's important to not forget these squareds. I sometimes do that when I'm doing this little estimation trick. So you can see where the 6's, where they kind of came from there. And then we've got 10 up to the negative 11 plus 24, and then minus 2 times 6, right? And so I've just rearranged that a little bit here. We've got negative 11 minus 12 plus 24. So that's negative 13 plus 24. Or actually, sorry, negative 11 plus negative 12 is negative 23 plus 24 is a positive 1. So we know our answer actually is about 1 times 10 up to the first power. And so we can actually estimate this whole thing to be about 10. And that actually matches up with reality. So if we look at reality, it's about 10 meters per second squared, roughly, if we do a rough estimate. And you can kind of see how these exponent rules apply in that situation to help us kind of understand what's going on there, right? You could look at a different one. So let's say that you have the same sort of problem, but now you have a different acceleration. So this acceleration of gravity is going to be slightly different here. And so we do still have the same constant for this second problem here, but it's basically slightly different. So like the radius has changed. So you could imagine that we have the same g, the same m, but now this radius is a lot bigger, so our acceleration should be smaller. So use a little bit of common sense with these numbers. So we've got the same gravitational constant here. We've got the same mass of Earth. And we're multiplying those, and that's all over the radius squared. And so this radius that we have in this situation is a little bit different. So if we look here, let's say we've got this times that all over our, what was that? 4.2164 times 10 up to the 7th power. So if we look at this number, you can see that we've got, yeah, it's kind of weird. We've got something in the denominator here that's 10 times bigger, and it's being squared, so it's going to be 100 times smaller. Our acceleration is what you should be getting. Just giving me a rough estimate. Like without doing any of this math, I can see that I've got our 6 times 6 all over 4 squared. So it's going to be a little bit different there. But then if we have our 10, in this case, this is 10 up to the negative 11 plus 24. But in this case, it's actually minus 7 times 2. So this is going to end up being 10 up to the, what is this? Minus 14. Is this minus 1 now? So this is 10, 14. Yeah. So this is -1 times 10, whatever this is. So instead of having 10 meters per second squared, this acceleration is going to be like 0.1 meters per second squared. Now we could actually get the number that goes in the front here pretty quickly too, if you just multiply the front numbers out. 6.67 times 5.98, and then we get that, and we're going to divide that by 4.2164. And then we divide that again by the 4.2164. And we get a value of about 2.2. Let's go with red for that. 2.243.5. And we can estimate that based off the sig figs that were given to us. So it looks like they're accurate to 3 sig figs. So this is going to be 2.24 times 10 up to the -1, which you could also write as 0.224. And I think the units for this was meters per second squared. So you get a rough idea of what your numbers should be with the magnitudes. You can kind of see how that works with that instance there in that physics problem. And then let's see, we've got like K equilibrium. This, I'm going to just get some rough estimates for this as well. So let's say that we're looking at this problem. We've got this reaction here. You can plug in those concentrations. It looks like we're going to have on the top for the products, it's going to end up being squared for one of these numbers. Our reactants are right here, our two numbers. So it looks like SO2, that's the 0.2 molar SO2, and then this is the O2 is 0.5 molar, I believe. And then this is 0.7 molar for the SO3. Yeah, okay. So without doing any math here, you can get a rough idea that this is 10 up to -1, K times 2, so that's 10 up to -2. So it's already kind of small. This is 10 up to -1, 10 up to the second power. So they're kind of canceling each other out in a regard there. And then this is 10 up to -1, but it's in the denominator. So I think K is going to be bigger than 1. And we can actually plug that in and solve for that. This, it might be easier to do just without doing any of the stuff, because these numbers are pretty small, but sometimes these can be very small or very big numbers, and it would be very, very helpful. So if I just do this calculation, I'm just curious, if we do 0.7 times 0.7 on the top, we get 0.49, and then 0.2 times 0.2 on the bottom times 0.5 is 0.02. And if we calculate that out, I believe that we've got it's the same as 49 divided by 2, which is 24.5, which kind of matches what I was thinking. Remember I said that I think that this is going to be bigger than 1. I'm not exactly sure how much bigger, but I was pretty certain that it was going to be bigger than 1. So yeah, it makes sense that our K is positive, or not positive, but bigger than 1 instead of less than 1, showing that's kind of favoring that product side, right? So that's one way to think about this. If we wanted to do this the other method that we've been doing, we've got like the 7 times 7 over 5 times 2 times 2, and that's being multiplied by 10 up to some power. So this was 10 up to the -1 times 2 on the top there. And then it looks like we are subtracting 1 there. Or like, yeah, we're just going to write that as a subtraction of 1 to account for that 1 there. And then this is, actually, sorry, no. This is 10 up to the -1, but it's in the denominator. So it is like subtracting -1, that first one. And then this is 10 up to the -1, but there's 2 of them. So it's -1 times 2, I believe. It can get a little bit confusing sometimes. So this is 10 up to the -1 raised up to that. Yeah, I think that this is a -1, so we are subtracting, but there is also another negative on it there. Yeah, because it should end up contributing in a positive way because it's small in the denominator. So you can think about it like that. So we've got our 10 -2 plus 1, and then it looks like plus 2. This is 10 up to the first power. So yeah, that's kind of like what I was saying earlier, where we knew it's going to be like 10-ish or bigger than 10 or somewhere around there. And then that's being multiplied by the 7 times 7 on the top, right? And then divide that by 5, and then divide that by 2, and divide that by 2, and that's 2.45. And then if you think about 2.45 times 10 to the first power, isn't that what we got earlier? Isn't that 24.5? So that's kind of how these things kind of work out, and you can kind of think through them. And then you can see, like in this case, we've got pKa, and these types of problems, they're involving very small numbers, right? So being able to keep track of your exponents on those types of problems and getting a rough idea, just a rough idea of what is reasonable is very, very useful. Also with your acid and base problems, this is kind of why pH and pOH, they add up to 14. It's a shorthand way of helping you keep track of those exponent rules. So if you had like ammonia right there and it's being dissolved, this is NH4, it's being dissolved and it's making this reaction happen. And so you can go ahead and find, using like your K equilibrium and everything, you can relate these amount of products even though they're super, super small. Like the pKa is a very small number. The amount of proton ions, very small number, but you can still relate them just like we did here with these larger numbers, because we have these exponent rules figured out. Okay. All right, that's it. Thank you for joining me. This has been Andrew McLaren. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.